Okay, let's get started. We're going to talk about the addition and subtraction of integers today. Integers, the definition of integers, the set of integers, which is written by this Blackboard Z, is the union of positive integers, the set of negative integers, and 0. So as you see here, I've got a little example of what it looks like. And when we're talking about integers, we have just now introduced negative numbers. And negative numbers weren't even introduced into any sort of math until like 600 CE, which means after the current era. So that is like 1200 years after whole numbers started being used commonly and being published into things that we've been able to research. Anyway, so here we are with negative numbers. And when you introduce negative numbers, a really good concept to get over to people if they have a hard time is to refer to it as money. It's a trick I've been using for years when students have a hard time with negative numbers and stuff. If you talk about it like money and refer to it as something that they already do tangibly in their own lives, they're quick about it. But that's not what we're here for. What we're here for is to look at the models and the methods used in the elementary schools. Okay? So we want to think about it as opposites, and the negative sign, which happens to also be the subtraction symbol, although I did notice in your textbook the way that they have been able to typeset it is a little bit smaller and a little bit above, and I don't really have that luxury with the software that I use, so you'll notice that I'm going to use just the same subtraction bar. And when you're actually writing it, you could write it a little bit smaller and higher to make the distinction. But for me to make the distinction and for my software to work, I'm having to put it always in parentheses, which is a great habit anyway. Anyhow, the negative symbol or the subtraction symbol, the negative sign, indicates that you're doing the actual opposite of the number. So let's look at a measurement model on the number line here for 3 minus 7. So as we recall from dealing with whole numbers, we always start at 0 to model that first number. And so I'm going to model the 3 starting here with a line at 0 and going 3 units. And if you were at school, you would have labeled every single one of these hash marks, but I'm a little bit lazy. And then we're going to pick up at the end of that 3, and now we're going to go 7 in the negative direction. So now we're going to go backwards 7. So 1, 2, 3, 4, 5, 6, 7. And our answer falls right here, which is -4. Okay, so this was our 3 in the positive direction, and this was our -7. And so now we can say 3 minus 7 is equal to -4. That would be the number line or the measurement model. Now, we can't talk about integers without kind of defining them with absolute value. So let's go ahead and introduce the idea of absolute value. So here's the formal definition of absolute value, and it's a lot of times it's confusing. So it should always be accompanied by a visual with a little example. So here it says for any integer x, the absolute value of whatever's inside that absolute value bar is equal to positive x if what is inside is greater than or equal to 0. And what is inside the absolute value bar could also be equal to -x if x is less than 0. And this is where the kind of the confusion comes. Because until now, you're probably thinking something like, well, the absolute value of 3 is equal to 3. And that's very true, but when we're dealing with the absolute value of an unknown, so in this case, let's do like the absolute value of something we don't know is equal to a number. What are the values that could go in here? Well, what could go in here to make this true would be 3, of course, right? Or the other number that could make that true is -3. And that's really what this is saying right here in just really awkward math language. And if we wanted to draw a picture of it, well, using our absolute value is equal to 3, then we know that that is true, but we also know that that is true because absolute value is just the measure of the distance from 0 to that number, and these are both 3 units. Now, distance is always, always, always a positive value, and the distance between any integer and 0 is actually the absolute value. So there is a difference between evaluating an absolute value expression and solving an absolute value expression. So right here in this first set of examples here, we are just evaluating an absolute value expression, basically applying the rule. So evaluating means we're just kind of applying the rule, and we know that whatever, if we have a number inside the absolute value bar, so here's our rule for absolute value. So the absolute value of -a is equal to a, and the absolute value of positive a is equal to a. In other words, no matter what the value is, no matter what the sign is inside of the absolute value, as long as it is just an expression we are evaluating, and notice this does not have any x's in it. This rule I wrote here has no x's, which means that this is an expression. Okay, so let's get down here and solve these real quick. The absolute value of 20 is just 20. We take whatever the number is on the inside and we remove the negative sign. This didn't have a negative sign. Here, the absolute value of -5 is equal to 5. And here, the absolute value of 0 is 0, but I put this one on here because it is to note that 0 can neither be positive or negative. It is, in fact, neutral. All right. Now, the last slide had that kind of official, really kind of hard to understand definition of absolute value, but here is an absolute value rule when we're solving an absolute value equation, okay? And it says if the absolute value of x or whatever it is equal to a number, then we get 2 answers here. We get the stuff inside the absolute value equal to positive that number, and the stuff inside that absolute value equal to negative that number. Now that should make sense because you've been trained coming up that you always get 2 answers when you have an absolute value. Well, almost always. There's not a whole lot of always in math, but it's a pretty steady rule that you could feel confident that you're going to get 2 answers. So let's take a look at how this is in practice. So I'm going to write that rule up here real quick so we can refer to the rule again. And so the rule says if the absolute value of something is equal to a number, then to solve it, we get two equations. We get that stuff inside the absolute value equal to the number, and the stuff inside the absolute value equal to negative the number. Now there's a couple of things to note here. First, that x can be anything. Okay, as you can see down here on a couple of on this example right here. So the x can be anything. The second thing I want to make note of is you never change the stuff inside the absolute value. And the third thing I want to point out, not that it's going to make any difference with the problems that you're going to be solving in this class, but I would be remiss not to say it is to apply the rule the absolute value must be isolated, which means it has to be the only thing on that side of the equation. Okay, now that I've got all those little rules out of the way, let's solve these problems here. So we'll look at this first problem. The first problem here says the absolute value of x equals 2. Now we need to just apply this rule. The rule says take the stuff inside the absolute value and set it equal to positive whatever that number that the equation is set equal to, and take the stuff inside the absolute value and set it equal to negative that number outside. And so here x is equal to 2 and x is equal to negative 2. Now, I forgot one of these rules over here, and it's a super important rule. And the rule is that a can never be negative. Which is another reason why you have to isolate the absolute value first. So when we look at this particular problem here, it is no solution because the absolute value of x cannot equal a negative number. Now, the answer can be negative, but when it is still in the form of absolute value, because of the definition of absolute value being the distance from 0 to some value, because that's the value and it can never ever be negative, and I think we will all agree, distance, you don't measure distance in the negative, then this is going to have no solution. Okay? Now let's look at this last problem I have over here, and I'm going to kind of draw a little box around it because I've managed to draw a whole bunch of stuff around, and I want to make sure that you see how this goes. Okay, so the first thing you want to notice is that this is truly isolated. There is no number added or subtracted to the absolute value. And so we're going to apply the rule, and the rule says take the stuff that's inside the absolute value. I like to call it the guts. And you're going to take your guts and you're going to set them equal to positive a, and this is our number a, so equal to 2. And then we're going to have this other equation. I'm going to write it down here because we're going to have to solve these equations. And we get the guts, x plus negative 3 is equal to negative 2. Okay, and then we'll solve this. I'm going to remove these extra parentheses. Remember, plusing a minus, adding a subtraction is the same thing as just a subtraction. Okay, and then to remove that, we're going to add the same number on both sides. So what we do to one side of the equation, we must do to the other. So now we have x is equal to 5. So there's one of our solutions. And now I'm going to clean this up and remove that. The steps to get to it is going to be the same. We're going to add 3 to both sides. And here we get x is equal to 1. So our answers are x is equal to 1 and x is equal to 5. Okay, all right, let's go. Okay, so let's look at some models for addition and subtraction of integers. So I'm going to talk about this thing called the chip model. And pretty much everything that I say about the chip model can be applied to the temperature cube model and the charged field model. Now, I'm mostly going to use the charged field model because it's easier to draw pluses and minuses than it is for me to draw different colored squares, and you'll see that. So I'm going to model the chip model for you with 2 different colors, but then after that I'm going to start just using the charged field model, but all of this is going to apply. Now, the chip model is when a student uses 2 colored chips, one color of chip to signify positive numbers and one color of chip to signify negative numbers. In fact, a lot of elementary schools have these 2-sided chips where one side's yellow and the other side's red, and that's what most students use. But this could be done with almost anything that you have plenty of 2 different colors, right? You could have one student could be using blue and green, another student could be using black and yellow. I mean, it could work out that way as well. Okay, so looking at this first example here, I'm asking us to do the 3 minus 7. Now, the whole idea of all of this modeling, once we've introduced this negative number, is neutralizing pairs. So keep in mind that every plus will cancel one minus, and the other way around, like every minus will cancel one plus. So this is the whole premise that we're going to lean on for these models. So if we look here, and let me use green for plus, and I'll use red for minus here. So looking at our chip model, actually I'll use red for plus and yellow for minus. Okay. Anyway, sorry, I should have decided that before I was sitting here having to decide it. So here's the idea. We're going to put in our 3 red chips. So I'm just going to make 3 red circles. And then the chips for our minus are, I'm going to use this yellow, and there's going to be 7 of them. And now what we get to do is cross them out one for one. So for this red guy, I'm going to cancel one yellow guy. For this red guy, I'll cancel one yellow guy. For this red guy, I'll cancel one yellow guy. And what's left is how many and what color is the sign. So we are left with -4 because that's our negative color. Okay, so temperature cube models, typically we use red and blue, red for positives, blue for negatives, you know, red for boiling water, blue for freezing water. And then doing a charged field here, we would use the pluses and minuses. So for this idea, we would say 3 pluses and 7 minuses, and then we can cross them out, and we're left with 4 minuses. Okay, let's get down to some nitty-gritty here. The definition of integer addition here. We're going to let m and n be integers as described. It's a 5-parter here. If m is an element of the integers, then 0 plus m equals m, which also equals m plus 0. This is the additive identity. 0 here is the additive identity. Means if we add it, it doesn't change anything. It's the identity. It doesn't change anything. Second one here, if m is greater than 0 and n is greater than 0, in other words, if the two numbers that you're adding together are positive, then the answer is going to be a whole number, which is also positive. Remember, integers are whole numbers that are signed positive and negative, including 0. So we haven't introduced fractions yet, no decimals. So if both of the numbers are positive and we're adding them together, we're also going to get a positive whole number. Then we have if one number is positive and the second number is positive, I might need to change that. Then the opposite, which is negative n, plus the opposite, which would be negative n, would equal negative the sum of m plus n. In other words, if you're adding the opposites together, you're going to get the opposite of the sum on the other side. I don't need to rewrite that. That is fine. Also, if n is greater than 0 and m is greater than n, okay, we got to put in those caveats there, then m plus negative n is equal to negative n plus m, which is equal to m minus n. And if you're so inclined to wanting to see some proof on that, I'm sure the textbook's got some proof on it. I almost did a proof, but I was kind of hoping to make this a short lesson here. And then finally, if n is greater than m and m is a positive number, then m plus negative n is equal to negative n plus m, which is equal to negative the difference between m and n. Blah. Anyway, yay. Okay, we did that. Let's talk about the properties. Properties are important. You'll spend time on that. That's what connects to the core properties of operations. Connect your things that you do in the classroom to the cores, to the core tasks. Objectives. Couldn't think of the word. To the core objectives that you have to map all of your classwork to. Coursework and everything you teach the kids. Okay, so here are the properties. For all integers a, b, and c, the following is true. The closure exists under addition. That means if a and b are integers and c is an integer and a plus b equals c, then that means that when you add two integers together, you get another integer. Yay. The commutative property, remember that is when you can change the order and it doesn't change the number. So 2 plus 3 is the same as 3 plus 2. Got it. Associative property, that means that you can group things around. I'm sorry. I got up too early this morning. You can group things around, okay, without it causing any harm. Identity property. A plus 0 is equal to A is equal to 0 plus A, which I just mentioned is the additive identity on the last page. The addition property of equity. This one's kind of new, but it makes sense. If A is equal to B, then A plus C is also equal to B plus C, because we've just said right here, because A is equal to B. So that means we can replace B for A. Okay. Now, for every integer of A, there exists a unique integer, negative A, and that is called the additive inverse. Okay. And the additive inverse just means if I give you 5, the additive inverse of 5 is negative 5. If I give you 0, the additive inverse is, Dr. Kelly, there are no additive inverses to 0 because negative 0 does not exist. If I give you the number negative 20 and ask for the additive inverse, you would say it would be positive 20. It's just whatever that opposite sign is, okay? Next says if you take the negative of the negative, you get a positive, okay? And finally, the last property down here, this last property pretty much allows you to factor out a negative number. Okay, and I'm just going to write here that 2 negatives equal a positive, because the negative of a negative is a positive. Excellent. Okay, so here let's take a look at what the additive inverses are to these, and the additive inverse is negative of what we've got there. So to truly do the additive inverse, we would go negative, being our additive inverse, of, and then we would write whatever that is up there. So that's a negative 3 plus x. And I know this seems a little bit nuts, but with the actual definition of additive inverse, it's what I've done here in purple. Okay, and then I'll clear this up. A negative of a negative, which I just showed on that last property, says that these guys cancel out, and so we're just left with 3 plus x. Okay, so to do the additive inverse here, it's going to be negative and some crap in parentheses, and the crap that goes in the parentheses in this case is going to be a plus this negative 4. Now, what is the opposite of a? That's going to give us negative a. And what's the opposite of negative 4? That's going to give us a positive 4. Let's do this one. It's going to be negative. This stuff here, let's see what that stuff's going to be. It's going to be this negative 3 plus this negative x. So the opposite of negative 3 is 3, and the opposite of negative x is x. Okay. Now, we did learn about the distribution over multiplication with whole numbers, and this actually applies also with integers. Now, one thing that I want to point out here, which is why we have all these examples that basically look the same, is we're distributing through this sign, okay? So be really careful. So I like to kind of make sure that that sign goes to everything that's inside those parentheses here. So this is going to equal 2, and then I've got a negative of a 5, so that's going to give us negative 5, and a negative of a negative x is positive x. And then we need to simplify this down, which means anything that's alike that we can collect up together, we're going to. So 2 minus 5 is negative 3, and there isn't anything to add to the x, so we'll just have plus x. Look at this guy here. We also have that negative sign that we need to distribute through there, right? The distribution over multiplication piece. So this is 5 because there's nothing happening with that 5. And now we're saying negative of the x is negative x. And negative of the negative 3 is positive 3. Then we'll put the things that are alike together. The numbers are alike. 5 plus 3 is 8. And then we're left with a negative x. Okay, here, this negative is right here in front, so let's be sure to distribute it to both things there. I'm going to write it down here because of my head being in the way. So this will be negative x, and the negative of a negative y is a positive y. And then we still have this guy left over. We need to drop down. And now when we clean this up, positive y and negative y go away, and our answer would be negative x. Okay, let's see here. Where am I? Oh, okay. I do want to talk about the chip model for subtraction, because the chip model for addition is very, very straightforward. But when we start talking about subtraction, we have to consider those neutral pairs. So I wanted to walk through this a little bit with a couple of examples. So the first thing, and I'm going to do this with a charged field model, okay, but I may use 2 different colors. Wait, let me find my pen. I couldn't find it. Okay, so the first thing it says for us to do is model the first integer. And you know, we read our problems here from left to right. So the first integer is 3. So I'm going to put in 3 positive 3's. Okay, and then the next thing it says to do is to model the second integer using neutral pairs. And what that means is you have to put in a plus and a minus. So I'm going to do my neutral pairs here in red. So here's my neutral pair. There's 2 of them. Now we want to perform the operation, and here the operation is to take away, take away 2 negatives. Okay, so I'm going to take these 2 negatives, and those come out. And then what's remaining is the solution. And so it will be all one sign. And here we have 1, 2, 3, 4, 5. So we can say 3 minus a negative 2 is equal to 5. All right, I know you've got a couple questions like this on your homework. Let's look at another one real quick. I snuck one in. This is our last slide here. I snuck one in down here on the bottom, and it says 5 minus a negative 6. So first we're going to put in our 5. And then I need to put in negative 6 worth of neutral pairs. Okay. And now what we're doing is we're taking away 6 negatives. So I need to remove those 6 negatives. Because this says right here, remove these. And that is 6 negatives. Or if we were doing color block, 6 reds or whatever, right? And then whatever's left over is what you have left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we can say 5 minus a negative 6 is equal to 11 positives. And if it was another case that the answer turned out to be a negative answer, if we started off with negatives or whatever, if it turned out to be a negative answer, it would be whatever the symbol is. But that's for another day. All right. I hope that you enjoyed. Have a good day.